Right, so welcome everyone, and thank you for joining this organized session on circular economy and material resources modeling. My name is Elisa, and I'm a senior economist at the OECD Environment Directorate. Maksym Chepeliev from GTAP is hosting and recording today's session and will help ensure that we keep our allotted time. Since Maksym will also be presenting, I'll help him with timekeeping during his presentation. Before getting to the presentations, please allow me to remind everyone of the following session protocol and etiquette so that the session runs smoothly. All attendees except the person currently speaking must remain muted. Unless otherwise noted, presentations will last 20 minutes. The session host will verbally prompt the presenter when there are 2 minutes remaining in their allotted time. When the allotted time presentation has lapsed, if the presentation has not already ended, the host will prompt again and will immediately move us onto the discussion period. Discussion periods will last 20 minutes and immediately follow each presentation. It is preferable for questions and comments to be entered into the chat. However, participants can raise their virtual hands as well. Session chairs will monitor the chat and participant list for raised hands during the discussion period. Read chat entries aloud and call upon the person with raised hands. And this will continue until the host will prompt the 2 minutes remaining of the discussion time. So following all but the final presentation, there will be a 2-minute transition period to allow the next presenter to prepare their presentations. And during this period, I will introduce the next presenter. I know it's early in the US, but I see a few participants. So I think we're ready to start with the presentation. And during this session, we will hear from 4 presenters. So without further ado, I would like to introduce the first speaker, who is my colleague, Ruben Bibas from the OECD Environment Directorate. He'll be presenting on modeling plastics use and waste in a CG model, methodology and baseline projections to 2060. The floor is yours, Ruben.
Thank you, Elisa. Hello, everybody. So I'll be presenting today work that we've led at the OECD on modeling plastics use and waste in a CG model. I'll present both methodology and baseline projections to 2060. This is work that's been done with a lot of colleagues, including Eleonora, Elisa, Martin, Rob, Daniel, and Jean, who are listed below. Sorry. I'm trying to get to the next slide. Yes. The objective of this publication is an outlook on plastics use, waste, and their environment and the environmental impacts of plastics. It's a new application of CGE to look at plastics use to create such an outlook to 2060. It's a CGE analysis based on ENV and the ENV linkages model that's developed at the OECD. So far, there are only a couple, maybe less than 10 studies, let's say, about plastics use in the future. But most of them are done with very simple assumptions, like plastics use is, or plastic mismanaged waste is following either population or GDP per capita, very simply. The policy relevance is linked to, in particular, to international goals. The G20 developed the Osaka Blue Ocean Vision to reduce the additional leakage of plastics to the ocean to 0 by 2050. And very recently, a couple of months ago, the UN Environment Assembly voted the resolution 514 that sets for a goal to ultimately end plastic pollution. So what's our modeling approach? So we're basing our modeling on the OECD ENV linkages model. And with that model, we're able to project regional and sectoral drivers of plastic use. And I'll explain in further detail in the following slides. Following these drivers of plastics use, we're projecting plastics use in tons by categories of polymers, applications, and linked to their to the most relevant economic activities. Following these projections of plastics use, using a lifetime methodology. So for each plastics and application, we attribute a lifetime, which allows us to project plastic waste in the future. Plastic waste is then differentiated by the different end-of-life fates. And finally, I won't present that today, but it's part of the publication that we're going from plastic waste, in particular mismanaged waste, to the environmental impacts in more detail. So today is really focusing on plastics use and plastic waste. For those of you who've seen our materials outlook that we published a few years ago, we've implemented a similar methodology where we linked plastic flows in megatons to the corresponding economic activities, or actually the economic inputs to economic activities. So, for instance, most of the plastic flows are coming from the plastic product sector, so RPP. And then, for instance, for building and construction application, it's only in the construction sector, and it concerns all of the polymers that we model, most of the polymers that we model. However, if you look at transportation other, for instance, which corresponds to all the vehicle parts that are made with plastics, it still comes from the plastic sectors, but it goes to a few different sectors that consume vehicles. And again, it's linked to specific sets of polymers. So we've created a mapping of all those flows based on the different applications and polymers, and linked to input and output sectors, which are the GTAP, based on the GTAP input-output matrices. Further to that, we have not only, we've also split the production technologies for plastics into primary and secondary. So primary is virgin plastics and secondary is recycled plastics. Those two production technologies produce the same good, plastics, which is considered very substitutable. We are splitting according to the volumes in tons, and with these shares for the different regions modeled. Quite interestingly, there are very high share, or very high share of secondaries, like higher than 5%, up to 9%, I think is the highest. In OECD EU countries, in OECD Asia, that's Japan and Korea, and in the other Asia countries, so China, India, and other non-OECD Asia. The rest of countries have much lower share of secondary, from 2 to 5%. And these are the basis for the size of the primary and secondary production technologies. The cost shares for these technologies are taken from Exiobase, and the salient facts for these technologies is that primary production uses most of the fossil fuels, and second, which is what you would expect because it's the main feedstock for primary plastics, and secondary uses about half of all of the inputs of the chemical sector. So its size, it's like lower than a tenth of the primary sector, but it still uses half of the chemical sector inputs. So that's for the calibration of the economic database. Now, how do we go from that to volumes? We calibrate a coefficient at base year. That's tons per dollar, and this is based on data by application and polymer. with the mapping that I presented a bit before. This coefficient is assumed to be constant over time, and therefore the growth of the RPP or CHM inputs to the other sector will drive the demand for plastics. However, what's not constant over time is the share of secondary and primary. Secondary production is assumed to grow with secondary economic flows, as we assume that all of the available secondary sector is used, all the scrap that's processed is used in the economy. The calibration of the initial volumes is done with waste collected for recycling and loss rates using a fixed point methodology. And of course, we check ex post that there is enough scrap available to produce the secondary plastics that we project. So for now, this is not. We would have been interested in putting a formal feedback loop in the model, but we haven't so far. And then primary plastic sector is the residual between the total demand and the secondary production. Going on to waste. So we used the methodology developed by Aguiar in their paper of 2017, where we attribute for each application distribution of lifetime for different uses. And you can see that for instance, for packaging, the average lifetime is less than a year. So most of all of the packaging plastics will be wasted between its production year and the next year, whereas other applications like transportation has a much longer lifetime of 13 years, industrial machinery above 20 years, and construction has an average of 35 years. And this means that plastics remains in use for several years. So because we can track when plastics was produced, we can also project the flows of waste that will be generated over time. And that's exactly what I wanted to explain in this chart. So the blue here represents primary production of plastics, which enters its use phase here. There is a huge volume of plastics that's like worth several years of production that's in use in the economy, and that's a stock. And between this stock and plastic waste, there's the lifetime approach that I just described. And what we did to be able to link secondary plastics to waste is that we have a certain share of plastic waste that's collected for recycling, and half or a bit less than half of that is lost and not used, not effectively recycled, but a fair part of it is recycled. So it first produced scrap and then secondary plastics, which then enters its use phase. So that's the main idea. And for these losses, they're described here. So it's by polymer, by country. It's quite interesting that actually loss rates are quite high for most polymers and most countries. There are very targeted plastics that are recycled quite heavily. For instance, high density polyethylene is one of them. Polypropylene and of course PET, those plastic bottles, with loss rates of plastic scrap that's much higher in OECD countries than in non-OECD countries. The richer you are, the more you can afford to waste plastic waste. I also wanted to draw your attention on the fact that the the recycling sector is in OECD countries very mostly a formal sector with losses that are more than 50% of the plastic flows. But in non-OECD countries, actually, it's quite exclusively informal sectors where the efficiency is much higher. So it's in link with this table where this is a summary of this table linking it to formal and informal sector. Going on to results. So the main driver of plastic use is the size of the economy. And here you can see that the share of global GDP by region in our baseline scenario. And Asia and Sub-Saharan Africa are the countries that are growing the fastest, increasing their share in the economy. In particular, you can see that like India here and Sub-Saharan Africa here are growing quite a lot. So here, not the other one. And those are the drivers of plastics use. If you look here at the corresponding plastics use, total plastics use projections, because the size of the economy tripled by 2060, the more or less plastics use also triple by 2060, with the growth being the fastest or the strongest in India, other Africa, and then other developing countries. It's also interesting to know that the growth is still quite strong in developed economies, such as OECD countries, USA, EU, and Japan and Australia. They're still quite important growth. This chart is a bit is a Sankey diagram of the different use, These two bars represents the share of polymers, and the size of the bar represents the growth. And then on the right, you have the different applications that are serviced by these different polymers. Packaging, construction, consumer products are the ones that are growing the fastest and driving the growth in these polymers. So it's hard to give a detailed account for every single polymer and application, but I just wanted to show how the granularity of our modeling is quite important, and we're paying extra attention to representing properly the different application and polymers that feed into these applications. Going on to waste, there's a tripling of waste generated as well, with a delay in time, but following plastics use. The different waste management categories, however, have a drastic change. So the first area in green shows recycled, whose share doubles by 2060 from 9% to 17%. Incineration and landfill have a quite constant share of about a fifth and half of total waste generated. And what's of most relevance for us, because we're looking at plastic leakage into the environment, and the largest share of plastic leakage comes from mismanaged waste, the last area in blue. So its share is decreasing from 22% to 15%, but because the size of plastic waste generation increases over time, the volumes of mismanaged waste increase. And that will have an impact on the leakage into the environment and the environmental impact of plastics. That's what I won't go into the detail of the environmental impacts. We can look at the publication, but I just wanted to show this chart to link plastic leakage per capita on the y-axis and and GDP per capita on the x-axis. And as you can see, if you will look at macro plastics, so the plastics that are bigger than 5 millimeter in size, which is the majority of plastic produced, you can see that overall, when you have a very significant example of the Kuznets curve, where for very low living standards, when it increases, leakage increases quite strongly. And that's what you can see, for instance, in Africa or Asian countries. But then when past a certain threshold, then the leakage decreases with increasing living standards. And that's where you can see all of the OECD countries, for instance, Canada here, USA, EU countries, that have decreasing leakage per capita over time.
2 minutes, Ruben.
However, this Kuznets curve doesn't appear, so far at least, for microplastics, which is smaller in size of a problem, but is a problem that's growing over time. And where for most countries with increasing income, there is increasing leakage to the environment. To sum up, the main messages of this presentation is that we've developed what we consider an innovative methodology. As I was saying, there is not much literature only linking plastic to population or GDP per capita or GDP, but it's the first of its kind linking in CG model linking plastics use to their economic drivers with a consistent economic and physical accounting. The main results for our baseline scenario is that in the absence of additional policies, plastic use is projected to triple. Secondary production, so recycled plastics, multiplied by 5, but still remains about 1/10 of total plastic use. The stocks of plastics in the economy will triple from 3 gigatons to 9 gigatons in 2060. And in line with that, waste will triple. What's interesting is that even in the baseline, the mismanaged waste and leakage, the growth of those two items is slower than the growth in use and waste. So there is an improvement already in baseline in terms of environmental management of plastics. However, because the use continues and grows over time, the accumulation of stocks in rivers and oceans of plastics increases quite strongly. Is multiplied by 3.5 from 140 megatons in 2019, so today, to about 500 megatons in 2060. So that really shows that there is indeed an issue with plastics in the future in the absence of new policies, which is why we also have worked on policy scenarios that will be presented by my colleague Eleonora tomorrow in the session 45. And for us, the next steps is a regional focus on Asian countries, ASEAN countries, sorry, and EU countries. I thank you for your attention, and I just wanted to also alert you to, or let you know of a more formal presentation that we're giving as part of the publication presentation on 21st of June with the registration link below. Thank you, and I'm happy to hear any questions or comments.
Elisa,
let me ask, is the floor open?
Elisa, you're muted. You were.
Maybe not.
Yeah, just.
Sorry, can you hear me?
Yes.
Can you hear me at all?
Yes,
So-
we can hear you. Yeah.
Alright, do
Max,
you have any, sorry, can I ask now?
I had Maksym had his hand up, but
Okay, good.
if you don't mind waiting,
That's fine,
Maksym.
yeah.
Yeah, sure. Yeah, thanks. Great presentation, and especially from the data methodological side, really impressive work involved. My question is more on the policy-related side, so maybe it would be discussed tomorrow. But so to me, it's always like surprising to look how low the recycling rate is in, for instance, in US or EU, and especially it's like in US, I think compared to 2019, in 2021, the rate has even fallen, like from 8% to 5%. So from the consumer side, seems to, at least we as consumers are diligently putting everything into the recycling bin, kind of, and so on. But still, the recycling rates are so low, despite the fact that there is infrastructural possibility to recycle, and from the cost perspective, I think it's also relatively feasible. So yeah, I'm just wondering, can you comment from the policy perspective of you, what's kind of wrong with the current set of incentives, and why we are so far away from where we would like to be?
So I'm speaking under the control of all my colleagues here who might know more than me. They're present, but for recycling rates, it's indeed true that they're very low, but they've increased quite steadily over time, and they're even in our baseline projections, they are projected to continue to increase quite a lot. So as I was saying, it's the number that increases the fastest in all of our projections. It's the recycling rates, and the production of recycled plastics. Recycling rates more or less doubles in all of the countries, and the production of recycled plastics is multiplied by 5. So it's still quite there is a significant increase. It's just it remains lower than primary, and there are a few issues that are also very different depending on the type of countries. For instance, for OECD countries, as I've presented, it's more of a formal sector issue, and what happens is that basically it's not economically interesting to recycle. It's just cheaper to produce new plastics. There is also an issue with contamination of plastics, which is easier to control with, basically primary plastic doesn't have that issue. So that's one thing. So the question is, how can we incentivize more recycling? And that goes into different direction. First of all, that the design of products needs to take into account that we want to recycle plastics. Then there is the collection for recycling that needs to increase. And third, the recycling, so the processing of scrap into recycled plastics also needs to be economically interesting. And if you want more detail on the policy instruments that we looked at, I would urge you to go to Eleonora's presentation tomorrow. But that's the three, we're looking at instruments that tackle all three of these issues. I just wanted to mention that in non-OECD countries, the problem is similar, but also has a different quality to it, because most of the recycling sector in non-OECD countries is still part of the informal sector. And there, what happens is that most of the time, you don't go through a formal collection system, but rather you have individual I don't know how they're called. I forgot the name. Pickers that would go into, landfills and would pick the plastics that they know are they're able to sell for recycling. And then that's, I guess, for us, the question was already a bit different, because there still we need to build already the infrastructure for waste management. So it compounds to the problem there.
Thank you.
There's another question from Pan.
Yeah, thank you.
Can't hear you.
Now, I just want some clarification.
On the video.
Okay, you can hear me.
Yeah. Yes.
Okay. So the plastics that you are examining is fossil fuel based, isn't it?
No, so we're looking at all types of plastics. I'll show you again this.
Okay.
Sorry, one sec. Here. So we're looking at, so we're looking in primary plastics. It's mostly fossil based, but there is a small part that's bio-based. We also looked at the possibility of expanding bio-based significantly, but there are hurdles, especially in terms of land competition and the environmental impacts as well as food prices impacts.
Yes.
And land availability. And we're also looking at secondary and so recycled plastics. So those are the main three channels for plastics.
So if the price of the primary inputs go through the roof, then the recycling rate will increase. So if the primary input is fossil fuel, and net zero kind of situation actually puts a lot of pressure on fossil fuel production, then that will accelerate recycling, plus development of non-fossil fuel based plastics. I don't know whether that is possible to the level that we are using plastics now.
So we looked, actually, thanks for the question. We actually looked into that. We included in our publication a sensitivity analysis to oil prices. And what you say is true, but to a much lesser extent than you would expect. Actually, the demand for primary plastics is quite insensitive to oil prices. Even if you increase oil prices by, let's say, 20%, the change in increase or decrease, actually, either way, the demand for fossil fuels changes, I think, by 1%. So it's very, 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 very insensitive to prices. And one of the reasons is that while it's the main feedstock, it's not a one-to-one correspondence with price. A lot of the price is the refining and the production of plastics. The feedstocks is not the main cost. The cost share is not.
For the item, the cost of plastic is very small.
Yeah.
The final item that is sold,
yes.
A small piece of handle or something else is plastic coated, and so even if its price doubles or triples, it doesn't matter.
Exactly. Matters little. Yes.
Yeah. All right. Okay.
Thanks.
So, thanks very much.
Well, thanks very much for.
Elisa, you're muted.
Sorry about that. Thanks, Ruben, and let's all give Ruben a virtual round of applause. Our next presenter is Alvaro Calzadilla from University College London, who will be presenting on the synergies and trade-offs between climate and circular economy policies in the steel industry. I see your slides up, Alvaro. So whenever you're ready, the floor is yours.
Okay, thank you. Can you hear me clearly?
Yes, yes.
Okay, yes. Thank you very much for the introduction, Elisa. I will present today a paper which talks about one of the questions that Home was asking. So what will happen if there is a climate policy and then fossil fuel production is somehow punished, and then what is the implications on the resource use and on different technologies that we have. And this is what I'm trying to do in this paper by exploring this type of synergies and complementarities that we can observe between climate policy and circular economy policies. So co-authors of this research are Matthew Winning and Teresa Domenech. The three of us work in the Circular Metal Center, which is created here in the UK, which is the UKRI Interdisciplinary Center for Circular Metals. And basically the vision of the Circular Metal Center is to go for a full metal circulation in which all the metal will be provided by a secondary production, and this will be achieved by reduce, reuse, remanufacture, recycling, and recovery. So part of this work is the work that we are doing for that Circular Economy Center, but also we have been working on this area the past 5 years. Let me see. Okay. Yeah, we all know that a pathway towards 1.5 degrees requires substantial economic, societal, and technological transformations. The transition towards and there is several technological and policy measures which targets mainly energy efficiency and clean energy, but this is not enough to deliver the Paris Agreement. So the transition towards a 1.5 degrees needs a deep and immediate emission reduction in heavy industry, cement, steel, and chemicals, but also in heavy-duty transport, trucking, shipping, and aviation. All these sectors are responsible for 1/3 of the global emissions. However, and basically the decarbonization potential of these sectors might lie in transforming linear economic models into closed-loop industrial systems and in shifting lifestyle patterns towards that direction. But actually, what we observe is that the current literature and the research community are fragmented. So there are a lot of people doing research on decarbonization and looking at the economic impacts, societal impacts, and the role of technology on achieving that. And also there is another group doing research on circular economy. But what is needed is an integrated assessment of circular economy policies, decarbonization policies, and sustainable development. And this is what I would like to add with this paper and this presentation, exploring these different synergies and complementarities. So I will start talking about how we assess decarbonization. So basically, we have this modeling framework in which we use a global energy model, which is the TM-UCL model, and we link this with a global economic model, which is the ENGAGE model. And what we do is we use common assumptions. So we use the same drivers, SSP, GDP, and population behind the SSP2 scenario for our business as usual scenarios, and we also use the same learning curve. So we basically use the same potential reduction in different energy technologies in the future. And once we have these common assumptions in our both models, the TIAM model produces a lot of results. And what we use in the engaged models is the emission reduction, the regional emission reduction, and the energy mix. So what we are trying to do is basically to simulate the emission reduction pathways that the global energy modeling is doing to achieve different temperatures targets like 2 degrees, 1.5 degrees. And we introduce this in Engage in order to have the same emission reduction, and we use a global carbon price in order to achieve that. But also what we want to represent is a similar energy mix. And then what we do in the Engage model is to use a fixed factor in order to adjust a little bit the energy mix and try to make as close as possible to the TIAM UCL model. In that way, the economic model will be very well informed by a bottom-up energy model. What we have here below is that is a work in progress. So what we are trying to do is then use the outputs of the Engage model to update the demand generator in the global energy model. So we will use changes in sectoral demand and changes in GDP to update this demand generator and start the process again. And here we can see some results. Here on the left, we can see global CO2 emissions produced by the TIAM model. And here we can see 4 scenarios. So here we can see how emissions increase a little bit compared to 2020. In the NDC scenario, we also have in the blue line achieving 2 degrees starting in 2030. So the reductions start in 2030. And then we can see here as well, reaching 2 degrees, but with an early action when we start reducing emissions now. And we can see also the pathway to decrease emissions to reach 1.5 degrees. And here below, we can see the results of the Engage model. So we have a lower level of emissions because we are only accounting for energy emissions. Instead, the TIAM model accounts for energy and process emissions. But we can see that the general pattern of these scenarios is very similar in Engage and in TIAM. And that's what we want to have because we want to simulate the dynamic transition according to the well-informed energy scenarios that the TIAM model uses. Of course, there are some differences. For example, in the 1.5 degrees scenario, the TIAM model reaches net zero or zero emissions in 2050. But because of the characteristic of my model in which I don't have negative emission technologies, it is very difficult to reach to that level. So my emissions decline in line with TIAM the first 20 years until 2040, 2045, but then it's very hard to decline more because I don't have those negative emission technologies. And here on the left, we can see the type of, it's not a calibration, but we try to have the same power mix in TIAM and in Engage. And we can see here that we achieve this, but also there are some differences because the Engage model, the global model, doesn't have all the technologies that the TIAM model has. But we can see in general terms that we do have the same type of energy mix in the in Engage as compared to TIAM. And this is an example for the USA power mix in 2030, if I'm right. And how we, so to carry out the simulations in this paper and presentation, we use the Engage materials model. The Engage materials model is a global CG model. It's a standard global CG model. It's a recursive dynamic. It is based on GTAP 9 Power 2011. But the main characteristic that this model has is that it represents still in a circular economy context. So here we can see the regional aggregation. We have 18 regions, 33 sectors, and 4 endowments. And what we can see is that we have a very good representation of the whole supply chain of the steel industry. So we have a split, and in order to have iron mining, then we have split the original iron and steel sector in order to have the production of primary steel, in order to have the production of secondary steel. And what we do have is also have an independent sector for steel scrap treatment and recycling. I'll talk a little bit more about this in the next slides, but also what we do have here in the model are the sectors which are downstream and uses iron and steel. These are metal products, motor vehicles, machinery and other equipment, and of course, construction. And in this specific version, we use the GTAP power in order to have a very good representation of the power sector in the model. All the database and modeling changes that we have done for the steel sector is an evolution of former publications that we had. And as I said, we started in 2017 to work on that. And this is basically the publications, and it shows also an evolution in the way in which we model and in the way in which we improve our database. And here we can see how primary steel and secondary steel is produced. So the main input for primary steel is iron ore, which can be produced using two technological routes, the electric arc furnace or the blast oxygen furnace. And basically, the share of these technologies will be region specific, and we can see this by the share of coking coal or electricity used in this production three, because we know that electric arc furnace uses more electricity, and blast oxygen furnace uses coking coal as a technology for melting basically the iron ore. And in the production of primary steel, what we observe as well is that they use the pre-consumer scrap. On the other hand, when we produce secondary steel, the main input will be electricity, because most of the main technology route is electric arc furnace for producing secondary steel. And of course, this is done by blending treated scrap and iron ore. And the amount that we get from treated scrap is basically produced by this individual sector that I mentioned earlier, and we are going to see how the production structure of this sector in the next slide. But what I would like to mention here is that both the primary steel and the secondary steel are constrained by an operating capacity which is specified for each year. And this capacity constraint allows us to simulate similar steel demand and also similar technology routes which we can observe in the International Energy Agency roadmap. Here we can see how the steel scrap treatment is produced, and basically the recycling sector will collect the scrap, and of course it will depend how much we produce of this steel scrap will depend on the scrap availability in the specific region, which is collected by the recycling sector, and we have a very simple production structure. And then in downstream sectors, what we have is direct substitution possibilities between primary steel and secondary steel. And the substitution possibilities here will be specific for the specific sectors, so will be different according to the sectors, because there are some quality differences between primary and secondary steel. The construction sector will be able to to absorb more of the secondary steel, but other sectors which require a more a steel with a higher quality will not be able to do to absorb the secondary steel if there is no technology which improves the quality of the secondary steel. And this is what we do in one of the simulations that I will talk later. We increase the elasticity of substitution in this industry 3 in order to model this technological change which allows different sectors to use more steel, thinking that the secondary steel will be of a higher quality. Let's have a look now to these two scenarios that I mentioned in the iron and steel technology roadmap, and we do have the stated policy scenario. The short name is STEPS. And then here we can see that the steel production grows from around 1.9 gigatons in 2019 to around 2.5 gigatons in 2050. And this growth is basically driven by the increasing demand of emerging economies. And we can see as well in this scenario that the dominance of China declines. Today represents around 50%. So 1 of every 2 tons of steel is produced by China, but then this dominance in the steel of China in the steel production will decline in 2050 to 30%. In the sustainable development scenario, steel demand grows to a lesser extent. We can see that only the steel demand is 19% lower that compared to the STEPS demand in 2050. And of course, there is also a different availability of scrap, which is shown here. And the scrap will decline as we are interested more in order to model the availability of scrap. We are interested in the end of life scrap, and we can see that the share of, the amount of end of life scrap will decline in the sustainable development scenario. But still, it is high because even if the production declines, there is a higher recovery rate in the sustainable development scenario, and the decline is not as much as the decline that we will observe in production. In the sustainable development scenario, the improvements in technology performance, which is this yellow area, and material efficiency, which is this purple area, deliver 90% of the emission reductions that is required to basically decarbonize, or the steel sector. It's not decarbonize, it's to be compatible with the Paris Agreement. So in the Paris Agreement, emissions in the steel sector needs to decline by 50% in order to be in line with the Paris Agreement. And this is the way in which the roadmap projects those declines. So we can see that 90% of this decline is achieved by material efficiency and technology performance in 2030. And this is basically going to be our year in which we are going to assess things. In the longer term, innovative technologies that integrate various carbon capture, use and storage and hydrogen technologies are required to decrease emissions further. And we are working on that version of the model, but in this presentation, I will focus only to 2030, looking at the 2 different technologies that I mentioned, the electric arc furnace and the blast oxygen furnace.
2 minutes, Alvaro. 2 minutes. 2 minutes left.
Oh, sorry, yeah. And basically, I do have 4 scenarios. One is the business as usual scenario, where I have basically just the indices, and the circular steel action is basically the step. So we have a high demand, but the same primary and secondary share. In the sustainable plus scenario, what we do have is basically a lower demand. So demand is aligned with the sustainable demand scenario in the roadmap, but also what we do is to increase the use of secondary steel in the downstream sectors. In the 1.5 scenario, here we model decarbonization, which reaches 1.5 degrees, but still we don't include here anything related to a circular steel. In the sustainable plus 1.5 degrees scenario, we include the climate policy to reach 1.5 degrees, and also we include a circular economy in the steel sector. So these are the results. So basically, here is steel production in the business as usual scenario. As we have seen in the steps scenario, the demand will grow, and this is actually represented here. But of course, what we don't observe here is an increase in the electric arc furnace or basically in the secondary steel production. So the share of secondary production is still the same, like 27%. In the sustainable plus scenario, so here basically what we do is to introduce this circularity, so we are able to produce more secondary steel. So we can see this here, that secondary steel increases because we are basically allowing for a circular economy in the steel sector. And when we introduce, in addition, a climate policy to achieve 1.5 degrees, we don't see that much changes in terms of how much is produced or in terms of the shares of primary and secondary production. But what we do observe when we introduce climate policy on top of circular economy is that emissions decline. So we can see that emissions decline even if the production is the same. Emissions decline in the sustainable plus 1.5 scenario, and as the production is the same, so we have a decline in the carbon intensity from 30% to 28%, if I'm correct. So what we observe basically is a decoupling of production and emissions. And here we can see the steel emissions. So in the business as usual scenario, which is the blue line, we don't see a decline in emissions. But when we introduce a climate policy reaching 1.5 degrees, we can see that emissions in the steel sector decline, but they start to decline a little bit at the end of the period. But if we introduce circular economy policies, and this is what we can see here in these two lines here, in these two scenarios in which we have circular economy policies, we can see that the emission decline in the steel sector is even larger. And in the sustainable plus 1.5 degrees scenario, for example, then we have a complete decoupling of emissions and production. And what is interesting is that this is comparing the steel emissions in the 1.5 degrees scenarios and in the sustainable plus 1.5 degrees scenarios, is that primary and secondary emissions declined by 4% between the period 2030, but it declines by 9% when we introduce or includes the production of steel scrap and also the production of iron ore. So basically, what we are saying here is that when we do have a climate policy and a circular economy, then we can achieve a more reduction in emissions. And this is my last results, and this is what we can see here. Here we can see the global GDP under different scenarios, and this is in the business as usual scenario. So if we introduce circular economy policies in the steel, then we can see an increase in GDP by 0.3%. If we introduce only climate policy scenario and compare this with the business as usual scenario, we will see a decline in GDP by 0.6%. But if in addition we introduce a climate policy, but also a circular economy policy in the steel sector, what we will see is that the GDP declines is lower. So basically, if what we are saying is that the cost of decarbonization will be lower if we have or if we push to circular economy policies in the steel sector. And here we can see that there are GDP gains when we move from the scenario 1.5 to the sustainable plus 1.5 scenario. So basically we can see gains when, in addition to the decarbonization, we have circularity in the steel sector. And this is a global increase in GDP, but of course, there are some regional differences. We can see that some countries like Indonesia and the former Soviet Union have a positive impact on GDP. Here is the change in GDP. And this is mainly related because they have a higher shift towards secondary production. On the other hand, we can see negative impacts for Russia, Brazil, and India, and this is mainly related with losses in iron ore exports because they are affected. Now, most of the production is basically done through scrap. And then they have a negative impact, which is basically observed by a negative change in the terms of trade. And China here has a negative impact because the share of or the importance related of China declines, and then there is a decline in the market share of China. And these are the conclusions. And basically the main conclusions that I want to focus is that circular economy industries facilitates emission reduction and lower the economic cost of the energy transition, as we have seen by the changes in the GDP. Climate policies penalizing fossil fuel use and renewable power production facilitates an early transition towards a circular steel industry, replacing coke or iron-based steel production with electricity and scrap-based steel production. However, this type of steel decarbonization is dependent on the scrap availability. So we know that there is not enough scrap availability to use more or to produce more secondary steel. So in the longer term, we have to rely on different technological innovations, which could be steel produced by hydrogen or steel attached to carbon capture, use, and storage. And thank you very much. Sorry for using more of my time.
Thanks a lot, Alvaro, for a very interesting presentation. I think we have time at least for a question. So please put your hands up if there are any. Ruben?
Hi, Alvaro. Thanks for the very interesting presentation. I had a couple of questions. The first is on what you called the demand generator. Can you just give us a bit more detail on how you calibrate the change in sectoral demands? And the second question is when you presented the production functions, I saw there were a lot of places where the substitution elasticities were zero.
Mm-hmm.
Difference between the different type of furnaces, and wasn't clear why.
Okay, thank you. Yeah, the first question is related to this slide, right?
Yes.
Okay, yeah. So basically, the drivers of energy demand in the global energy model, TIAM, is sectoral demand, which is attached to GDP changes. at the end. So a higher economic activity will imply a higher sectoral demand of different transport, I don't know, heating and so on. And this will basically in the TM model have a demand generator, which will drive all the optimization of the energy mix in the TM model. And they use in general GDP, which is then converted or translated into changes in these demands, which are then fed into the model. And what we want to do is, instead of them using the GDP behind some SSP scenarios, use the output of the engaged model, which already account for market adjustments and price differences, and then use these as an updated of these demand. So probably in some sectors, the demand will decline or the demand will increase. And this is what we want to do in this type of feedback effects from the global economic model to the global energy model.
Maybe I misphrased my question. The question was more on what are the drivers of the sectoral demands in, I guess, in Engage rather than in the demand generator itself. Like, what are the drivers of the determinants of the different,
okay, yeah, for which sectors? For the energy sectors or for which sectors do you mean? The energy sectors or specifically to the primary and secondary steel production?
I meant even more widely, it's just, if I understand correctly, TM works probably the same way the IEA model works. They're using, the value-added growth of services, industry, and different
Yes.
sectors. I just was wondering how you calibrate the evolution of the shares of the different sectors in Engage.
No, basically what I use is also changes in GDP and population as the main drivers for the Engage model. And what I'm taking only from TM is the dynamic decline in emissions, in regional emissions, and the energy mix from them. So this is what I'm taking from them, trying to align the way in which they see the decarbonization happening, and the different scenarios are trying to align the energy production, specifically power production in the model. Then the demand, as in other CG models, will depend on the GDP calibration and the population. Mm-hmm.
Thank you.
All right, thank you very much. Alvaro, if there are other questions, I suggest to go through the chat, so maybe Alvaro can answer there. Because in interest of time, I'd like to move to the next presentation. But first, let's give Alvaro a virtual round of applause. Thanks very much for the presentation. So I'd like to ask Maksym Chepeliev from GTAP, who's the next presenter, to present instead of his colleague Angel, who is unfortunately sick. Maksym will be presenting on the EU Green Deal and circular economy transition, impacts and interaction. I see your slides up, Maksym, so please go ahead.
Yeah, thanks a lot, Elisa. As Elisa mentioned, I will be presenting instead of Angel, and it's a joint work with colleagues from GTAP Center, with also Angel and Dominique, and also colleagues from the World Bank, Tom Farrell and Andrea Liverani. So we are grateful for their support from the World Bank for this work. As an introduction, coming from kind of a big picture, we observe increasing material extraction, and apart from impacts on emissions and climate mitigation, it's also a big issue for their ecosystem and ecosystem services. As we have already seen from Ruben's presentation and also from other studies, projected increases of income and population are expected to put even further kind of pressure on the material extraction and use. So based on some estimates, more than doubling by 2050. And of course, here we also see interactions with greenhouse gas mitigation goals. So of course, if we would produce more plastics and more primary iron and steel, it would be harder to achieve mitigation goals. So in this regard, studies suggest that we need an absolute decoupling between GDP, ORs, and economic indicators and material use, which has proven to be pretty hard to achieve, as we have already seen from the previous two presenters. So what we are trying to look in these studies to examine interactions between circular economy and climate mitigation policies, as Alvaro has presented, but we also then moving into more detail into circular economy specific policies, because just jumping a little bit ahead, we find a relatively minor impact from mitigation policies on the circularity. Yeah, so we find that there is a need for additional policies, and that's where the main focus of our study is. Yeah. So just a brief overview of and we focus this study on EU, and we also look specifically into several Eastern European member states like Poland, Croatia, Bulgaria, and Romania, which in general have recycling rates lower than EU average. So those are good case studies to see how the things would evolve there and what policies can be implemented to help these countries to move forward at a better pace. So, and on this slide, you can see recycling rates across different EU member states, and these are for all materials, not only for metals or plastics, but kind of an aggregate indicator. We see some improvements over time. So we can see changes between 2010 and 2019, but they are not kind of incredible in the sense that EU average circularity use rate has increased around 2 percentage points over 10 years. So still pretty challenging. So on the legislative point of view, few EU countries have circular economy strategies. So and policymakers are not always well equipped with a sufficient knowledge of how circularity principles work and what are the potential implications of these policies on the economy. So this particular kind of point is especially important for country-specific work. So we also have in parallel projects that now focuses on Turkey. And that's one of the reasons why country-specific studies are also important in this regard. So I'll briefly present our data side since we already presented a preliminary data work on the last year's conference, but we did some major improvements compared to that particular presentation. So we are splitting a number of sectors in GTAP, and in a sense, our approach is similar to the combination of what Alvaro and Ruben had been presenting before. So we are splitting extraction as extraction into different ores, so non-metallic, iron ore, aluminum, copper, other ores. We're splitting plastics into rubber products, primary, secondary plastics, and also recycling. We're doing some split for iron and steel, also primary, secondary, recycling, and casting. And then a large split is done for the non-ferrous metals, where we distinguish aluminum, copper, other metals, and non-ferrous metals casting. And then for each of these three types of metals, we have primary, secondary, and recycling. Yeah. So as a result, we apply this to the GTAP 10 power database, and as a result, we have 95 sectors for 141 regions. And we call this database GTAP Circular Economy, so GTAP CE database. You can also see here on the right hand side a representation of primary versus secondary emission intensities, also split across different scopes, so scope 1, 2, and 3. And we see that there is in across all materials except maybe to some extent plastics, there is a very substantial gap between primary material emission intensity and secondary. So potentially there is a scope for emission reduction from switching from primary to secondary production. Okay, so our scenario framework, and this is a little bit busy slide, but I'll try my best to explain it. So we start from the business as usual scenario. And just to mention, so we're using the envisage computable general equilibrium model for this particular study. So we start with the business as usual scenario. Then on top, we implement the EU Green Deal mitigation goals, which is consistent with Fit for 55 targets, so 55% reduction in emissions in 2030 relative to 1990. And then on top of this, we implement a number of circular economy policies. So we distinguish them into two broad groups. So one is a demand or use pattern shift, so demand or use side policies. So there we have changes in consumer preferences. So, and we have specific quantifications for these policies. So essentially it's a reduction in final consumer demand for material goods. And then we have a compensating increase in the demand for other goods. And we do it through the phantom tax implementation and essential preference shifter in their model. We also have a design change use pattern shift, which essentially says that with some specific improvements, you can use less. So, for instance, assume you have a car which has a different design and uses less plastics and metals, but then it uses more of R&D inputs and design kind of consulting inputs. So essentially, there is a shift from material to the service use. We have also a lifetime extension scenario where we assume that, again, through this consumption pattern shifts, people use the same commodities, but they use it longer. So in our case, kind of 20% of time longer, but then we have a compensating shift towards increasing demand in other goods. And then we have a set of fiscal measures plus on top border adjustment taxes, where we combine different taxation and subsidization scenario imposing extraction taxes, production taxes or subsidies on primary versus secondary materials. And then we also have border adjustment taxes to look into their potential options to avoid leakage. And then we also look into different revenue recycling mechanisms, such as reduction in labor taxes. And finally, we have a combined scenario where we combine several of these options. So you can see it's a pretty complicated framework in the sense of scenario setup, and I'll try to kind of present key messages that come out from this framework. But before moving to the policy scenario impacts itself, just a brief overview of what's happening in the baseline. And we are running the model till 2030. And one particular feature that we have introduced recently into this framework is that we trace all the material use weights in primary commodity equivalents. So we have all quantities of non-metallic minerals, metallic minerals, essentially fossil fuels, in primary commodity equivalents, and then we trace how their production-based versus consumption-based material use changes, so what we see here is that in the baseline scenario, we see that production-based material use increases in most EU countries, so dotted line is in EU average, but even in most transition economies, it also increases. It somewhat reduces in Poland, interestingly. But then when we look into the consumption side, we see that it's essentially what's happening is that there is a shift towards like imports of materials embodied into imports, into trade. So from the consumption point of view, in all countries, material use increases in the baseline. So the baseline doesn't look kind of even close enough to what we would like to have, this absolute decoupling here. Okay, so what would happen if we impose our mitigation efforts? And this is an carbon pricing mechanism imposed on fossil fuel combustion. So what we see here is percentage change in primary material use in Europe across different material categories. So we see that for the fossil fuel materials, quite a substantial reduction. Yeah, so for instance, coal from the production-based perspective reduces 30%, natural gas 20%, oil 12%, somewhat lower because of the transportation sector, harder to abate. But then there is substantial leakage. So what we see here from consumption point of view, fossil fuels reduce much less. So EU just shifts to importing. But it doesn't help to reduce material use from other very broad and important categories such as metal ores and non-metallic minerals. So these are essentially, are impacted very insignificantly with the carbon pricing. Okay, so what we look next is, and here I present their baseline. So this is production-based material use. Solid lines is the baseline, and dotted line is the combined scenario that combines several circular economy policies. And on the next slide, I'll explain what it includes. But essentially, it includes production taxes to primary commodities, subsidies to secondary production, and also shifts in demand patterns. So the bottom line here is that with this combined scenario from the production point of view, we are able to achieve absolute reduction in material use by 2030. Still, non-metallic minerals seems to be the most kind of challenging case here. So that's the main message from this slide. Okay, so now this is again a pretty busy slide, but I'll try to decompose it. So what we see here is a change in material use over time. Yeah, relative to the reference year, relative to 2021 in 2030. And this is decomposed by different types of materials. So yellow is non-metallic minerals. So for instance, the first column is baseline, production side accounting. Second column is baseline, consumption side accounting. So what we see here in the baseline, non-metallic mineral use increases from production side 12%, consumption side 18%. Use of other materials, and this is as a share of total material use. Yeah, so essentially non-metallic minerals dominate the total use, and they increase in the baseline. Fossil fuels kind of fall, and they're so this is an aggregate increase are indicated by these red triangulars, and black rectangulars, they indicate a change in the GDP material intensity. So what we see in the baseline, production side material intensity of GDP falls, consumption side increases. Yeah, and then we look into different scenarios and we kind of measure how this changes. Yeah, in different scenarios. So both from consumption and from the production side. So one observation here is that non-metallic minerals, this yellow kind of part of the bar, seems to be the most challenging to reduce. Yeah, so we see that coal and other fossil fuels relatively easy to reduce with different measures, both consumption and production side. Non-metallic minerals the most challenging, but with this combined scenario where we combine preference shift, design change, and tax on the extraction, we are able to kind of bring non-metallic mineral use close to their kind of reference year, 2021, and substantially decrease use of other materials. Still, leakage is a concern. So with consumption side, kind of not much of an impact here. Note that the GDP material intensity almost in all scenarios decreases quite substantially. So we do observe relative decoupling almost in all cases, yeah. Okay, so now in terms of the impacts, essentially how much would these different measures cost? Green is, and this is all measured relative to baseline. This is percentage change in real GDP indicated by columns. And we also, so I'll first discuss the percentage change in real GDP. So the cost of Fit for 55 package is around 0.7% of GDP. And then, for instance, this preference shifts adds an additional 0.4% cost to their EU mitigation scenario. So in general, we see that the circular economy policies are on par with their EU mitigation policy costs, or even lower of a lower cost. The combined scenario, which is the most ambitious, costs around 1.7% of GDP. Still, when we convert it to growth rates, it's not large, 0.2% reduction in the growth rates over this 10 years. So one concerning thing, though, is we also trace a wage gap difference. So how the relative wages of unskilled or low-skilled workers change relative to the high-skilled workers. So, and this is indicated here with this red rectangular. So if it's negative, it means that the wage of high-skilled workers increases relative to low-skilled. If it's positive, so you see in this several scenarios, it's slightly positive. It means that low-skilled workers kind of are gaining relative to high-skilled workers. And what we see here is that the circular economy transition has a relatively high chance of increasing the wage gap, which is somewhat concerning. So before moving to conclusion, also, I just wanted to point out one thing, is that we also looked into the case of labor recycling, the collected revenue from taxing primary production through the reduction in labor taxes. And we find that in this case, we can achieve double dividends, so that their GDP essentially increases relative to their EU mitigation case, yeah. So this is potentially a kind of attractive solution. So fiscal measures combined with revenue recycling through labor taxes could provide double dividends. And this way of revenue recycling has been also proved to be kind of economically efficient in a number of other studies that focused on recycling climate mitigation, kind of carbon taxation revenue. So it's consistent with the literature, though in the different area. Okay, so to conclude, what we find is that climate and circular economy policies are complementary, so there is no silver bullet. We can implement a pretty ambitious mitigation policies, but still it won't improve substantially reduce material use intensity, and not even close to achieve an absolute decoupling. So we really need to combine these two strains of policies. And this would help to reduce not only emissions, but also there is this important part of ecosystem services, environmental pressure from mining and related issues. So in our combined scenario, we have been able, when we combine both demand side policies and fiscal measures, we were able to achieve absolute decoupling in aggregate material use by around 6% reduction in 2030 relative to 2021. So we also find that measures must be targeted in a sense that depending on what type of measures we apply, whether it's a lifetime extension policy or fiscal policy, they can help to focus on different materials. So with the demand side measures, essentially there is no one benefit of demand side measures is that they in general prevent leakage, because it doesn't matter whether you source your material domestically or you import it, you still reduce the material use, while the fiscal policies, they have a relatively large potential for leakage. And that's the next point here. So we might consider benefits and drawbacks of the border adjustment tax, which we also modeled in this study. Just because of lack of time did not present this. Also, a point of double dividends. So reducing labor taxes can increase both GDP and welfare, and allow to reach double dividends in terms of reducing material use and boosting the economy. But we found this a point of potential concerning point of increasing kind of skill premiums, so which could result in regressive distributional impact. So that's something to further explore. We also currently working on the number of extensions to this work. So I already mentioned the country-specific focus on Turkey. We are also working on splitting building sector into conventional and green across countries. So trying to approach this non-metallic mineral use point, and also representing cement and concrete production using conventional and green kind of technologies, also linked to this building sector representation. And I'll stop here. Thank you.
Thanks very much, Maksym. Are there any questions? Well, while people think, I have a question. So I would like to ask to clarify a little bit how you modeled the policies on demand and use patterns, because I didn't quite understand how you model them and then how you calibrate them. So if there are costs or investments or something.
Yeah, so that's a good question. In this particular case, we assumed essentially cost neutral. Well, it's not really cost neutral, because we imposed an phantom taxes to target the specific changes in their demand patterns. So, for instance, we set a target of reducing material use by households, let's say by 20%. So we imposed a tax on an endogenous tax to reach that reduction in material use, and then the collected revenue was given as a subsidy to the rest of materials, or to the specific set of materials in case of let's say design change. So that leads to the increase essentially in the demand for other materials. So if we would have a specific cost of this move, it's possible to calibrate it to the selected cost, and that's indeed a very interesting also question. Yeah.
Great, thanks very much. I think Ruben has another question.
Yes, on the results you presented in the last slide, the next to last slide, the one where you show the GDP impacts per the different instruments. I was wondering if you have an explanation for, maybe I misunderstood, but my understanding is that the sum of all instruments would show a cost much higher than the combined scenario. And why is there such a difference in
the combined scenario includes three of these. So it's preference shift, design change, and extraction tax. So here we show 7 different options and sub-options, including border adjustment taxes. And then the combined scenario includes this preference shift, then design change, and extraction tax. So indeed, the overall cost of this scenario is somewhat lower than just a linear combination of 3 of these. But it's not a linear combination of all of these options. So,
but it's still 3% versus 1.5%.
So yeah, it's 1.7, and here we would see about 3%. So well, not because it's extraction, about 2.5. So well, apparently there are interactions. So if you reduce your material use from one policy, then let's say extraction tax would have a lower impact because you are already using less of let's say plastics or some non-metallic minerals. So that's, and yeah, it would be interesting to decompose it. Yeah, so we can probably run a number of simulations to decompose how this combination of policies results in a lower cost in the lower total cost. That's a good point. Yeah.
Since we still have a few minutes, I'd like to ask another clarification question. So you show a wage gap here and mention in the final slide about the skills premium. Can you maybe explain a bit on what you did on the labor markets modeling, if you differentiate different types of skills, and if so, how many?
So we have skilled and unskilled, so two, and then we have an unemployment closure. So essentially, this is just a gap between skilled and unskilled wages. So interestingly, there were some empirical studies that also find this point that by moving to a more like secondary production, potentially with a higher technological level of implementation, there could be this skill bias. So so it was interesting kind of to find the same results, though from a much more aggregate model that like ours. Yeah.
All right, thanks a lot for clarifying that. I don't see any other questions or hands up. So I'd like to thank you, Maksym, for a great presentation, and let's give Maksym a round of applause. Our next and last presenter is Alessandro Gatto from Wageningen University, who will be presenting on Eat Good, Less Waste, Global Food Loss and Waste in the context of healthier and more sustainable diets. I don't see your slides up yet, Alessandro, but feel free to... Yeah, I can hear you, yes.
Okay.
Yeah,
yes.
I can see your slides now. Thanks very much. Please go ahead.
Thank you. So the work I'm presenting today is basically an overview of a recent paper I wrote with my two PhD supervisors, Marek Kajver and Hans van Meel, on the trade-offs between the transition to healthy and sustainable diets and the generation of food loss and waste along global supply chains. To give you a bit of context, transition to a healthier and sustainable diet, which is by definition a plant-based diet, has the potential to increase the availability of food loss and waste biomass, which can generate two effects. It can stimulate the food loss and waste reuse in those regions where recycling facilities are available, and reusing food losses is economically a good opportunity. But can also turn up to be a curse in those regions where reusing food loss and waste is not an economic possibility, as increasing losses and waste can lead up to increasing air and soil pollution, in turn reducing the positive impact of a sustainable diet. So to assess such trade-offs, is necessary to first understand the magnitude, the composition, and the location of lost and discarded food along food supply chains, while simultaneously accounting for changing agents, actors' behavior across the economic system and the interactions along the supply chains. For doing this, today we encounter two main challenges. On the methodological side, we know that technical studies often offer good physical data, a good overview of material flows, but unfortunately disregard agent behavior and interaction of different agents along the supply chains. We well know that our general equilibrium models are offer dollar-based quantities, which tend to be insufficient to assess global challenges related to physical flows and biomass flows, and especially in the context of circularity. And therefore, for effective policy design, it's crucial to track the physical amount of biomass flows along the supply chains in order to also provide a consistent linkage with technical models and tackle food loss and waste with adequate technologies. On the data side, challenges rely in the unavailability of food loss and waste data at the global scale. So there is a conflicting, first, there is no common definition, no reliable global measurement available. Today, there is contrasting issues, methodological approaches, and specifications of supply chains in available studies, which lead to uncomparable and inconsistent estimates. And the most adopted estimates available today at the global level from Gustafsson have resulted to be largely inconsistent, and also are presenting severe limitations in terms of data coverage. So for this, the focus of this study focusing on tackling challenges on two sides. On the capturing a physical biomass flow, we add the consistent tracing of biomass physical quantities to a global general equilibrium model, basically assessing biomass competition through the global economy and quantifying magnitude, composition, and geographical availability of biomass flows, which is a prerequisite to then tracing food quantities from farm to fork, identifying production, intermediate demand and use, and final food use. To this, we link a new up-to-date global food loss and waste database, basically capturing actual food intakes, computing food loss and waste based on actual food intakes rather than food supply based on the food balance sheets, which omits retail and consumers' waste, which can be substantial in certain countries. And with this, we identify the physical magnitude and composition of food loss and waste, outlining the different stages of the supply chain where it occurs, and identifying the location of this waste and providing therefore a multidisciplinary assessment key for effective policy design. So from the data issue, we compile an up-to-date global database, performing a literature review on the percentages of lost and waste of total food weight discarded along supply chains. We adopt a consistent food loss and waste definition in line with the Sustainable Development Goals and with the FAO food loss related indicators. We expand, so we start with the FAO food loss and waste database published in 2019 and track the data gaps of the database, on which we perform a literature review, screening more than 300 sources and enhancing, as you see in the figure, the overall data coverage of the FAO database. From the modeling side, we start tracing physical quantities in a general equilibrium framework, building on an approach developed by Kuiper in 2022, which takes the social accounting metrics of the GTAP database and detracts all the monetary components, so taxes, margins, and so on, obtaining measures for dollar-based quantities. So the author defines a balancing equation, which it's simple as total production equals intermediate demand, both domestic and imported, plus final demand, also both domestic and imported. So this balancing equation is kept as a benchmark to test if the model consistently holds the balance in monetary units across simulations. And later also in physical units, because then we take this physical balance and we derive the Leontief inverse matrix to obtain a full overview of flows through the economy, including sector by sector, sector to sector trade, which is quite key for understanding food waste. We obtain so the coefficient reported in equation 1, which is specified over 5 dimensions. 3 regional dimensions that indicate region of production, region of intermediate demand, and region of final consumption, and 2 commodity dimensions which identify the primary production commodity produced in a production region and the final consumption commodity consumed in the final consumption region. So by taking the equation 1 and dividing it by total production, we obtain the shares specifying how a single unit of output flows through the global economy. This serves to integrate physical biomass data, which we derive from the FAO. And from this, we define physical food flows across the global economy, preserving material balances in monetary and physical units. So respecting the balancing equation you see here at point 1. To the food flows across the global food supply chains, we integrate our food loss and waste database. and basically are capable to quantify global food loss and waste at each stage of the supply chain, identifying the magnitude, the composition, and geographic allocation. So, for example, if a banana is produced in Colombia, then exported to the United States, where it's processed as a banana bread, and then further re-exported to Europe, we are capable to basically trace in primary equivalence this banana, even when it enters in processed food or in food services, and compute the losses that this product generates at the different lifetime until it's finally consumed. So to give you a practical example, here you see food loss and waste generated by final consumption of processed vegetables in Europe. And so you see that the final consumption of processed vegetable generates different stages of the food supply chain, and for different commodities, certain tons of losses, mainly occurring in Europe, but also relevant in agricultural stage of the North American Oceania, or in Latin America and Caribbean. So the simulation in this analysis builds on Magnet using GTAP 10 data in 2014. Magnet is a general equilibrium model from Wageningen Economic Research. We have 8 global regions complemented by 4 countries, which represent a proxy for different income levels. The time frame of analysis goes to 2030, and we compare an SSP2 baseline, business as usual baseline, against our sustainable diet scenario, which is here defined as the 8 Lancet dietary scenario. So, as we know, the 8 Lancet diet has been proved to be unaffordable for several low-income regions. Therefore, we define a scenario which is moving halfway to the 8 Lancet diet. So we do not impose a target, the full 8 Lancet diet, but only halfway towards the 8 Lancet diet, because we were seeing that the food diet was not implementable as it was too expensive for certain regions. So we do this by defining the percentage change in per capita household consumption required to meet the 8 Lancet dietary targets. We split some of the 8 Lancet commodities between the GTAP commodities. So, for example, sweeteners are split between raw sugar and processed sugar. And we also define the intakes from food services and processed foods in primary equivalence. And this results quite fundamental, because accounting also the intakes through different channels cumulatively poses a constraint on intakes which is more severe than other studies have done, which have disregarded basically the consumption through these channels. So we impose a constraint that the total intake via primary processed and food services has to always be below the 8 Lancet, equal or below the 8 Lancet intakes. Moving to some results, we can see something on global food loss and waste magnitude. So we see that in our baseline, consumption in 2030 expands with increasing population and incomes, generating an 11.6% increase, reaching 2.6 billion tons. So, and especially in low-income regions where increasing domestic and export demand enlarges agricultural production losses by an average 15% and reaches the biggest global hotspot of food loss and waste generation in 2030. Moving to the Lancet diet instead has quite a positive effect on global food loss and waste magnitude, because we see that the decrease in food consumption forced by the diet reduces total food loss and waste by 17.2%. The less trade imposed by the diet, especially of export from low and mid-income regions of plant-based foods, decreases losses at the farm level production, so in agricultural production with a minus 18.5% and post-harvest with a minus 29%. As well as in high-income regions in which, especially at the later stages of the supply chain, like consumption, decreasing food intakes with the diet decrease by 1/3, so minus 35%, the magnitude of losses. So in the graph here, you see grams of food loss and waste generated per capita per day. And you see that, for example, big exporting countries like Brazil account for high levels of food loss and waste in physical terms. In terms of food loss and waste composition, we see that in the baseline, increasing food demand, especially in high-income regions, expand the shares of processed foods, of meat, and of fruit and vegetables. And in low-income regions, increasing intakes often associate with increasing amounts of meat consumption, so therefore result in increasing shares of animal products and cereals within generated food loss and waste. In the Lancet scenario, instead, we see that the Lancet enlarges fruit and vegetables and cereals within global food loss and waste, because by definition is a plant-based diet. Replacing animal source food and animal source food shares within losses, and overall decreasing the loss of calories embedded in food loss and waste. At the same time, we see that for some low-income regions, which are currently consuming below the Lancet recommendation, some shares of animal source food increase, like for example for fish or for dairies, while decreasing some shares of other crops currently consumed largely above the Lancet diet. An interesting result is on global food loss and waste location. So we see that in a baseline, food losses, excluding food waste, which is by definition only generated domestically, food losses embedded in imports by income regions represent, by high income regions represent 46.9% of total losses. So these losses are not located in high income regions themselves, but are located in exporting low or mid income regions, which produce these goods and export them to high income regions. Therefore, we see that, for example, domestic losses for big export-oriented regions like Brazil or Ethiopia in a baseline in 2030 reach an average of 95.4% of the total losses. In the Lancet scenario, instead, we see that by decreasing food demand, therefore decreasing trade, the Lancet decreases highly perishable plant-based foods, reducing this spillover effect of high-income regions generating losses abroad. Despite so, for example, imports demand of animal source food decreases the most, we see that even with the Lancet diet, high-income regions still account for significant shares of total losses in mid and high-income regions. So this spillover effect is still relevant, despite is quite reduced. In terms of locations, it's also interesting to notice out of the total losses generated, which share occurs abroad and which share occurs domestically. So we see that the Lancet diet, again, the decreasing imports of plant-based food from high-income regions generates decreases also farm-level losses in exporting low and mid-income regions. But overall, we see that there is domestic shares of losses increasing, given the fact that countries now produce slightly more domestically than importing. And we see that, for example, in low-income regions, higher consumption levels coupled with trade substitution effect, so slightly more trade in plant-based food rather than animal source food, result in higher domestic losses. So going to conclusions and discussion, we can derive some conclusions based on the Sustainable Development Goals. So we see that in terms of food security, healthy and sustainable diet, as the Lancet diet decreases food trade, therefore potentially increasing domestic food availability. We see that the diet assists the reduction of total food loss and waste generation, simultaneously reducing the loss of calories in nutritional terms along the food supply chain. With regards to environmental sustainability, there is a potential problem related to the geographical mismatch between the availability of food loss and waste and the availability of proficient recycling facilities, which risk to compromise the environmental benefit of transitioning to a healthier diet. In terms of food loss and waste, we identify key global hotspots in farm-level losses, in farm-level stage of the supply chain in low and mid-income regions, and in the later stages of the supply chain, such as consumption stage in high-income regions. In this, it's important to notice the spillover effect high-income regions exert on low-income regions. So we see that as a lot of losses from high-income regions are located abroad, such high-income regions may relatively easily meet their Sustainable Development Goal 12.3, which aims to halve food loss and waste, contemporaneously compromising the path of low and mid-income regions in achieving their Sustainable Development Goal, as generated food loss and waste. National Sustainable Development Goals do not account for import-embedded food loss and waste. Towards a circular bio-based economy, so for the reuse of food loss and waste as a potential production input, we see that the Lancet diet enhances the quality of food loss and waste, increasing plant-based food shares, which compared to animal source food is highly is more easy to be employed as a production input. But at the same time, the spatial availability of food loss and waste located in low-income regions and in mid-income regions may limit the creation of domestic material loops for circular purposes, which often require high technologies not available in low-income regions. So for building on the limitations and taking next step to expand the current research, it's necessary first to implement this accounting in a dynamic modeling framework, because currently the computation of the Leontief inverse can only be done ex post, or it's done ex post and would be value added to be able to target it during simulation. We aim to develop food loss and waste abatement cost curves, and together with Maksym Chepeliev, we are aiming to embed, fully integrate this food loss and waste tracing into the new GTAP 11 database release with a special issue on food loss and waste. And for sure it would be value add to apply such findings on in a circular economic framework. And on this, we are working on a forthcoming paper on a circular economy for livestock sector, where we take this food loss and waste, and based on the location and the availability and on the composition, we try to substitute animal feed with potential food waste. And also this method could also provide a new input for the tracing of other non-bio-based materials, such as plastics or metals, which are always interesting to trace along global value chains for enhancing the transition to circularity. With this, I conclude, and I thank you for your attention, and I welcome any comments, questions, or suggestions.
Thank you very much for the very interesting presentation. There's a question already from Maksym. So Maksym, please.
Yeah, thanks, Elisa. Thanks, Alessandro. Great presentation. So I was wondering if you, also in line with our previous discussion on this topic with you, I was wondering, did you look into what are net caloric supplies that are resulting from this particular approach in terms of net food consumption? Because I think that would be an important comparison point just for understanding how robust and consistent are the estimates here. Because as we know, in some, especially lower income countries, FAO reports gross caloric consumption close to 19 or 200 or 2000. So if the share of waste and loss is, let's say, over 20%, that would result in undernutrition, let's say, for the entire country, which is probably not the case. So I was wondering if you can comment a little bit on this.
So yes, as you well know, there is a big mismatch between nutrition data, available nutrition data on intakes at household level and the food loss and waste estimates that we have today available. and such that if we tried to combine those, we would end up with no, for example, obesity problems in the United States, or with certain low-income regions consuming more than European countries, and so on. So that's for sure a big issue, and I haven't tested it in this particular case. I have done some nutritional accounting only for the generated losses. So basically tracing the nutritional content of the foods that actually end up being lost, and therefore computing what's the nutritional loss there. It's something that has to be done on this side to understand effectively what are the net intakes, net of all these losses, because the problem is with the food balance sheets is that they get a net of losses but not net of waste, and therefore they omit these last stages of the supply chain, which are quite significant. But yes, this moment in time, for sure, it requires either a more calibrated estimates on what actually the intakes are, on so the gross intakes for specific countries are, or some stronger assumptions on certain data, so that for those countries which we find inconsistencies between the two types of data, either we need to descale the focus, so go into a more national level surveys on food loss and waste, because at the end of the day, we for this study, for example, we bring it to aggregated level, so also at a regional level. So maybe if for certain countries that have such inconsistencies, it would be nice to have a more specific food loss and waste data, and also a lot of estimates are also based on assumptions given the unavailability of data. So also there something can be done in terms of intervals to see basically a range and understand when we manage to have consistent intakes with which shares of food loss and waste. But for sure is one of the hot topics, let's say, around this debate. Yeah,
thanks. Just one quick kind of more follow-up comment. So one of the interesting features that we have been observing is that although we apply food loss and waste shares at an aggregate regional level, let's say EU average, or because of the different composition in food consumption, then the resulting net caloric intake at country level, let's say in EU, varies very substantially. And then the question is like, is it really something that is observed, or is it due to kind of implementation of this aggregate regional waste and loss share? So yeah, that's just related to this point. Yeah, probably also something to kind of verify and also look into.
Yes, it's a really nice point, because despite you keep the shares of food loss and waste, let's say, on a regional level, you still have, as you're saying, different food consumption trends. So the food supply itself changes quite a lot by single country, but also the trade-related food supply. So it's in the sense that the exports are quite different in Italy rather than in the Netherlands. And so you will end up with different amounts of losses at different initial stages before these exports are done. So that's something that I let's say it's a good result in this study itself, and was quite fundamental for obtaining this result. Was the food tracing rather than food loss and waste tracing itself, because the moment you manage to have a biomass tracing first, so you first understand biomass competition, so how food competes with feed and with other industrial biomass uses and these substitution effects, then you manage to understand the actual food supply, both the base year and the 2030 or 2050. And then you see basically how food supply either expands within total biomass or shrinks, and also how it differs. And then to that, how that influences the overall amounts. So the problem is not necessarily on the shares of food loss and waste, which literature advocates to use, because they're found to be more consistent over the years and more reliable rather than other type of food loss and waste data. But then, yes, the dynamics behind it in terms of food supply are quite crucial for the difference for like an heterogeneous accounting by country.
Thanks.
I'd like to ask a question as well. I was wondering, since we're talking about healthy diets, if there was a way you could link the simulation results to the health benefits from a healthier diet, using, for instance, global burden of disease. Like, could you, for instance, link it to lower instances of obesity or malnutrition, and see the actual health benefits in, quantitative terms?
Yeah, I mean, at the end of the way the Eat Lancer diet is framed is basically, again, a plant-based diet, which has been done in this way because of both health and environmental issues. So you see that meat, it's quite taken away, and there is the amounts that are basically recommended are mainly the highest amounts that are recommended of food are cereals, fruit and vegetables, and tubers, and so on. So in this analysis itself, we just impose it and do not do any sort of let's say policy analysis or path analysis of how we are going to reach this type of consumption. So we just it's let's say the type of shock implemented here is the type that tomorrow everybody wakes up and starts eating sustainably. And if that's the case, what would be the consequence for food loss and waste? But for sure, we would derive analysis on the health implications, which are related to all the nutritional values that countries derive from the intake of this bundle of products. So for sure, you can associate that like a physical food supply with all sorts of nutrients, and from that derive health-related analysis.
And similar question, could you quantify, like verify the changes in emissions? Because I understand that emissions from consumption of meat would go down, but you would possibly have higher emissions from land use. So I don't know if you have that in the model or not.
I do have that, but I haven't included in this analysis. For sure, at the moment you have physical amounts tracing, you can start linking basically land use or greenhouse gas emissions, and you see that. And since this is basically, I would call it extended life cycle assessment. The moment you start decreasing meat consumption, you also see that some land, the agricultural side gets freed for feed. So there is all these trade-offs are for sure accounted, but it's also nice because you can expand really much in the direction that you want the moment you have a solid physical accounting of something. And this for me was a value added, because then with technical models, it's easier to implement a discourse, and especially for circularity, where you have to have the substitution between secondary materials and primary materials, and you never know to which extent, on an economic side, on a value-based term, that could be feasible to replace a specific, let's say, in the case of the study that I'm doing now of replacing a primary feed with losses, food losses. Economically could be feasible, but then in physical terms or in nutritional terms for animals, you could be killed because basically supplementing, maybe you don't have the enough physical amount of losses to reach the nutritional supply that an animal would require to be fed. So no, for sure the analysis can be expanded with all sorts of indicators. It's just, I think, for circularity, it's just crucial to do it on physical quantities together with the economic value-based amounts. Otherwise, only doing it on value-based terms risks to be inconsistent from a technical side.
I saw in terms of next steps, you're citing including plastics, amongst other materials. So to finish the session with the question on circularity within the session, I think your model setup would be nice to also maybe take into account, the trade-offs for bioplastics in terms of then wooden emissions, etc. So, I understand you're planning to do something similar for plastics, but would you do a separate model version for plastics, or still include this part of the analysis and add plastics?
So basically, the way it's constructed now, the moment you have consistent production data in physical amounts for specific materials, with the application of this Leontief inverse, you're basically capable to decompose the flow of plastic through the global value chains. And so you see that plastic production, but as well, with bioplastics, probably there it's more complicated in terms of getting data in terms of production, and so as for making a physical merging, that's a quite necessary point to have consistent physical data. But yeah, the moment you see basically the life of let's say a ton of plastic going through the economy, you could potentially start mapping where this plastic ends up, or where the plastic scraps are, so where you can start enhancing policies for recycling, also of metal scrap, for example. And then together with biomass for plastics, for example, you could do the same thing. And then at the moment you have a nice, let's say, mapping along the global value chains of where the plastic is most used, and where, for example, plastic residues are, or where bioplastics is available in physical terms, then you have this potential primary and secondary material information, such that you can start understanding, okay, this is a key hotspot for this, so we should aim for a policy in this region at this stage of the supply chain. So for me, it's more for calibrating, let's say, policies on this side, rather than always counting on again value-based amounts. Yeah, but indeed it would be nice, for example, with secondary plastics, to see the substitution capabilities also in technical terms.
Okay, thank you very much for the thoughts, and let's give Alessandro a round of applause too. That presentation concludes the session on circular economy and material resource modeling. Please help me in thanking our presenters for their valuable contribution and presentations. I would also like to thank the organizers of this thematic session, so Maksym and Ruben. This is the second year we have this session at GTAP, and I find it's helping with increasing the amount of people who work on a circular economy. This topic is not using a CG model, but it's providing a lot of very good policy insights. So I was glad to see that there are over 30 participants in this session. Thanks to everyone who participated, and thanks everyone for joining us. And I hope you enjoy the remainder of the conference.